Hi everyone. Today we're going to talk about Chapter 5, Probability Densities. 5.1, Continuous Random Variables. So in Chapter 4, we learned about discrete distribution. Okay, so do you still remember what is discrete distribution? Okay, so for, let me put it here, for discrete distribution, okay, we have the PMF and we have the CDF. Okay, so PMF is Px equals to K, CDF is Px less than equal to K, right? So what is the picture of the PMF? Oh, they're actually points, right? So they are like points, and when you add them all up, okay, when you add up all the probability, that equals to 1. Okay, and how about the picture of the CDF? Well, the picture of the CDF is, for example, here, then before this point, we have 0, and then this point, we have here, okay, to the next point. So it's like a stair shape function, okay, and let's say it's like this. So it's non-decreasing and it's greater or equal to 0 and is continuous from the right. Okay, so this is a picture of the discrete distribution, the PMF and the CDF. Okay, so today we're going to talk about the continuous distribution. All right, so you might think about, oh, what is the difference between discrete and continuous? I would say think about if the problem is asking you the number of apples and the number of person, the number must be a whole number, right? You cannot have half of a person. We cannot cut the person in half, right? So those are discrete distribution. But such as time, weight, and we can have like 5.2 minutes, or we can have 14.3 pounds. Okay, so those numbers not necessarily has to be an integer. Okay, so those can be continuous random variable. So today we will talk about definition of continuous random variable. Okay, all right. So let me make it smaller. Okay. All right, so definition, let x be a random variable. If a function f from real numbers to real numbers satisfies the property that probability of x less than equal to b equals to the integral from minus infinity to b f of x dx for all b in the real numbers, then f is the probability density function PDF. So for discrete random variable, we have PMF, probability mass function. Then for continuous random variable, we have the PDF. It's not Adobe PDF, okay? This is probability density function. So let me draw a picture. Let me use a different color to indicate that. Okay, so the picture is like that. Okay, instead of discrete points, the PDF for continuous random variable is going to be a continuous function. Okay, and let's say if we have the b here, then we have the property that probability of x less than equal to b is the integral of minus infinity to b of f of x dx. So, which is this area. Okay. All right. So here are some remarks. First, for all a and b that are real numbers, suppose a less than equal to b, then the probability of x in a, b is then probability of x less than equal to b minus probability x less than equal to a, right? A, B, you want to include the b but exclude the a, so what do? You use less than equal to b, subtract less than equal to a, right? You subtract the a, so the a is missing. Okay, so then this guy is, so from the picture of the PDF, okay, we have A here, B here, okay? So how do you compute the probability between them? Well, that is exactly this region. So that is the integral from A to B of f of x dx. So in chapter 4, when we work with discrete distribution, we use sum, okay? Like the mean and variance, we sum all the values that x times the probability of x, okay? And in chapter 5, for continuous random variable, we're going to use integral. So discrete, sum, continuous, integral, okay? So second remark. For all c in the real numbers, probability of x equal to c is the integral from c to c f of x dx. And do you know what that is? Think about it. From c to c is actually the area of a line segment. But a line segment is one-dimensional. It has no area. So that's why the probability at a single point is 0. Well, this is the very big difference than the discrete distribution. Because discrete distribution, the probability of each point is positive. Okay? But here, for continuous random variable, the probability of a single point is actually 0. Okay? 3, if x has a PDF, okay, then for all a less than equal to b, probability of x in a, b, that is equal to probability x in a, b, that's equal to probability x in a, b, that is the probability of x in a, b. Okay, because the probability at a single point is 0. That's why the boundary does not matter. Okay, so that's why they are equal to f of b minus f of a, where f is the CDF. We'll talk about that later. Okay, so do you remember for discrete random variable, this four intervals we actually have different answers? Okay, but for continuous random variable, they are all the same. Okay, all right. I want to put one more remark here. Okay, let me use the color indicate. So remark 4. You can see the properties of CDF. Okay, so properties of PDF. Okay. Do you remember the properties of PMF? We have two properties. First, of all the points, P of x is greater or equal to 0, and then when you sum up all the probability, that equals to 1. So here we have the same property. First, f of x is greater or equal to 0. Second, instead of sum, we're going to have integral. Integral from minus infinity to plus infinity. F of x dx equals to 1. Okay, so those are the properties. So let's look at example 1. Check whether the following function is a PDF for some random variable x. Okay, so what does it look like? Okay, where when x is not equal to when x is not from 0 to 1, the function is 0. So let's draw a picture here. Okay. All right. So this is x. Okay. This is the y. We want to and write f of x. Okay. So when x is, so this is 0, this is 1. When x is not equal to 0, 1, we get 0. Okay. When x equals to, when x is from 0 to 1, we follow this formula, 1 over 2 square root of x. Well, if we plug in 0, we can see, oh, 0 in the denominator. That's not good. But actually, when x is getting close to 0, okay, you can see we have 1 over some number getting close to 0, and that is infinity. Okay, so actually when x approach 0 from the right, we actually get infinity. And we can plug in 1. When we plug in 1, we get what? 1 over 2, right? So this is 1 over 2. We are right here. And then it goes up to infinity. Okay. All right. So this is f of x. Okay. So how do we verify is PDF? Let's check whether it satisfies the properties of PDF. First, you can see the picture f of x is greater or equal to 0. Yeah, that's obvious. Second, we want to integrate from minus infinity to infinity of f of x dx. Well, you can see when x is outside of 0 to 1, f of x is just 0. So that's why this integral is just the same as we evaluate the integral from 0 to 1. And what is the formula? 2 square root of x dx. So while we see the constant multiple, we can pull it out. So that's 1/2. And we make it into the standard form. This is x to the what? Okay, pause here and answer my questions. Yes, minus 1/2 dx. Okay, so what do? We add 1 to the exponent divided by the exponent. Evaluate from 0 to 1. Wow, 1/2 cancel. So we have square root of x evaluate from 0 to 1. Well, the square root of 1 minus square root of 0. Wow, what is that? 1. Yay! So we actually prove that f is a PDF for some random variable x. Okay, so this guy means when random variable. Okay. Next. Remark. Oh, so I also put a remark here. Okay, good. Fact. If f is a PDF of a random variable, then for all the reasonable b, so b is any set in the real numbers, then probability x in the b is the integral over the set b. So b could be an interval and it could be a union of disjoint intervals. Okay, next. Definition. Random variables which have the PDF are continuous random variable. Okay, so here's a definition of continuous random variable. We have the PDF is a continuous function. All right, next definition, the cumulative distribution function, CDF. Okay, so CDF is actually the same name. We know we have PMF for discrete random variable. We have PDF for continuous random variable, but we have CDF for both of them. Okay, so CDF is, so we still use capital F of x. That's the probability x less than or equal to small x. So if x has the PDF, then it equals to the integral. So because now if x is here, you want to find the probability of x less than or equal to less equal to the small x. So that's why that is the integral from minus infinity to x of f of, you don't want to call it x again, so you want to use another letter. Maybe you can use y, or maybe you can use t, doesn't matter. Okay, so notice that the derivative of the capital F is small f, right? That is because of the fundamental theorem of calculus. Okay, so that's why if f is continuous, then we have the derivative of the capital F is the small f. Okay. Fact: capital F is a CDF for some random variable if and only if the following happens. So we already talked about this before. So first, when x goes to minus infinity, the limit is 0. When x goes to positive infinity, is 1. The limit is 1. And f is non-decreasing. Okay, it's not strictly increasing. It's non-decreasing. Okay, it could stay the same and increase, and stay the same and increase. Okay, and f is continuous from the right. What does that mean? It means it's like okay, it's like this, like that. So it's continuous from the right. Okay, the function value equals to the right side of the limit. Okay. Alright, we denote f of x plus be the right side of the limit at x. We denote f of x minus be the left side of the limit at x. If f is the CDF of x, then f of x plus is f of x. Okay, because you see this picture. Okay, so you can see the right side of the limit equals to the function value. You see the solid dot here? And then the left side of the limit is f of x minus p of x equals to small x. Okay? So that is the probability at that single point x. Alright. Let's continue with example 1. Find a CDF. Okay, so given a PDF, how do we find the CDF? Integrate it. Okay, so know that the derivative of the CDF is the PDF. So the integral of the PDF is the CDF. Okay, so if the problem is giving you the CDF, then you differentiate it to find the PDF. If the problem gives you PDF, you integrate it and then you can find the CDF. Okay, let's see. All right, so we can start from the picture. Do you remember the picture of it? Is like that, is 0 there, and then like that, this is 1/2, and is like 0 again. Okay, this is the picture, right? Okay. All right. So that is why we can see if x is less than or equal to 0. Okay, if x is less than or equal to 0, we get f of x is 0 because small f of x is 0. Okay, if x is between 0 and 1, then f of x is going to be the integral from 0 to x of small f of, let's use another letter. Let's use y or t, doesn't matter. Okay? So what is that? That is 1/2 integral from 0 to x, y to the minus 1/2. Okay, so we add 1 to the exponent divided by that exponent, evaluate from 0 to x. That cancel. So we plug in x in the y. So we have square root of y minus square root of 0. That's square root of y. Square root of x because we plug in x. Okay. And what happens if x is greater or equal to, I just realized that this is solid dot. This is the open circle. Okay. Oh, did I make this mistake? Okay. Yes, I make this mistake as well here. So, yeah, we're gonna be very careful. At 0 and 1, this is solid dot. And then at 1/2, this is open circle. Okay. Alright, so when x is greater or equal to 1, okay, what happened? Wow, you can see f of x is going to be, when you plug in 1 in the square root of x, it becomes 1. But after 1, your PDF is 0, so you're not adding anything to it. So capital F of x is just stay at 1. Okay, so let's summarize. F of x is 0 if x is less than or equal to 0. And a square root of x if x is between 0 and 1, and is 1 if x is greater or equal to 1. So that is the CDF. All right. Okay, let's look at example 2. We want to find the CDF of this function. First of all, let's draw it. Okay, so let's draw it here. Alright, so let's use different color to draw it. Okay, when x less than or equal to 0 is 0. So less than or equal to 0 is 0. And include a 0 point. Okay. When x is greater than 0 is 2 times e to the minus 2x. So when you plug in 0, you get 2 times e to the 0. E to the 0 is 1. So 2 times 1 is what? 2, right? So we have 2 here, and we have a open circle. Okay, what happened when x goes to infinity? Well, do you know, like, this is e to the x, right? When x goes to, so you can see that when x goes to infinity, the minus 2x goes to minus infinity. So your picture is like here. So it actually goes to 0. So it goes to 0. This is the picture. Okay, we want to find the CDF. All right, let's look at the picture and start. We can see that if x less than or equal to 0, it's gonna be 0, right? And if x is greater than 0, f of x is the integral of, because it is non-zero at 0. So 0 to x, 2 e to the minus 2, let's use a different letter, y. That is, what is that? That is 2. Do you remember what's the integral of e to the minus 2y? You have e to the minus 2y, and then you divide by negative 2. When you differentiate, you multiply by negative 2. When you integrate, you divide it by negative 2. So evaluate from 0 to x. The 2 cancel, so we plug in x first. And then minus, negative become plus. We plug in 0. E to the 0 is 1. Oh, okay. So this is what we get. And you can see when x goes to infinity, this guy goes to 0. So our answer goes to 1. Okay, and it makes sense, right? Because to be a CDF, when limit when the limits when x goes to infinity, it should be 1. All right, so let's put them together into a piecewise function. It's 0 if for x is less than or equal to 0 is 1 minus e to the minus 2x for x greater than 0. Okay. All right, so that is example 2. Okay, let's continue to look at example 3. A boy plays outside and chooses uniformly at random a time from 0 to 1 hours when he wants to return. If he doesn't return in 45 minutes, his mother brings him in. Sorry, missing it. Let x be the time when the boy gets home. Find the CDF for x. Okay? So please pause here and try to work on this problem. This problem is actually quite interesting. Okay, so first step. This is what the boy thinks. Okay, so he plays outside and choose uniformly at random a time from 0 to 1 hours when he wants to return. Okay, so that's why when what does this boy thinks? The boy thinks that this is the PDF. It's he chooses uniformly at random a time from 0 to 1 to return. Okay, so that's why any time that's from 0 to 1 is gonna be uniformly. Uniformly means they have the same probability. Okay, so this guy, they have the same probability. What is this number? Remember that the area is 1. Okay, so this length is 1, and we need the area, because the area is the probability, the total probability. It has to be 1. So it forced the height. The height has to be 1. So that's why this is 1. Okay, so this is the PDF. Okay, and you can, if you want to use a formula to denote that, well, that would be f of x is 1 if x is between 0, 1, and 0 if x is not in 0, 1. So this is how we denote. Okay, and then what is the CDF for that? Okay, the CDF for that, let's draw pictures. Okay, let me use different color. Okay, the CDF is the integral. So when x is less than 0, because the small f is 0, so it stays there. And then when x is between 0 and 1, you integrate 1. How do you integrate 1? Integral 1 is what? X. So it's a line, right? A line. And then after 1, the probability is just gonna be, the total probability is gonna be 1, so it stays right here. So f of x is 0 if x is less than 0, and it equals to x. So actually x for x is 0, 1, and it's 1 if x greater than 1. Okay, so this is what the boy thinks. Okay, but now what happened? After, so here, without the mother, this is gonna be like what happened. But now the mother says that, okay, so mother brings him in after 45 minutes. So what is 45 minutes? So here, because the unit of the time is hours. So what is 45 minutes? Is 45 minutes. How many minutes in an hour? So we want to cancel the minute and get the hour. So 1 hour has 60 minutes. So minute cancel. 45 over 60 is what? 3 over 4 hours. Okay, so mother brings him in at the 3/4 hours. Okay, so that's why what is the new CDF? Okay, here's the new CDF. Let me indicate the difference. Okay, let me use black color. Okay, so this is the real CDF from 0 to 1. Okay, so the boys. Okay, the boys think like that. Okay, and then let's say this is 1. This is the boy thinks. Okay, but now because of the mother right at 3 over 4, let's say this is a 3 over 4. So here, this is still the boy what he thinks. Okay, so it continues to get to here, but the mother said, okay, after 45 minutes, no matter whether you're outside or inside, I make sure you're gonna be at home. Yes. So right at 3 over 4 hours, the mother say, no matter what, you have to be at home. So that's why at this time, it's gonna be like that. You must be at home. Okay? So that's why this is the picture. Okay? The boy. This is 3 over 4. And then after the 3 over 4 hours, the boy has to be at home. Okay? All right. So now what is this guy? So let's draw it. So oops, let me use the green color. Okay. So f of x is 0 if x less than 0. Okay, and it's equal to x if x is between 0 and 3 over 4, not include the 3 over 4. Okay, and it's gonna be 1, so the boy has to be at home. The problem is at home, right there. Okay, that is when x is greater or equal to 3 over 4. All right. Yes, that is because of the mother bring him in. Okay. All right, so what we can see here. Okay, so we mark. You can see in this picture, f of x is not continuous. Okay? It is not continuous. So that's why, we have a theorem from calculus 1. Differentiable implies continuous. So not continuous implies not differentiable. Okay, so that's why df dx does not exist. Okay, so you cannot, you won't get a PDF. That's why x has no PDF. Okay, because it's not PDF, so x is not a continuous random variable. And furthermore, x is not a discrete random variable as well, because it's time. Time is not like whole numbers. So this is an example that we can have a random variable that are not discrete and not continuous. Okay. All right. Next, let's talk about the expectation, the mean. Okay, the expectation of a continuous random variable is still we call mu is e of x. And instead of sum, okay, if you can remember what we have for discrete, so for discrete random variable x, we have the mean is the sum of x times p of x equals to small x. Okay, so here for continuous random variable, instead of sum, we have integral. Okay, and we use x times the PDF. And furthermore, if x is a continuous random variable and let g be a function from r to r, then you basically just replace x by g of x. And that's similar to what we had before. Just replace the sum by the integral. Okay, and then the n moment, we have x to the n here. And for the variance, similar, we have the integral of x minus mu squared. Okay. And we also have this fact. Variance of x is the second moment minus the mean squared. Okay, and e of ax plus b equals to a times e of x plus b. The variance of ax plus b is a squared times variance of x. So actually the proof are identical. You just replace the sum by integral. So they work the same way. All right, so let's continue with example 1. Find the mean and variance for the following function. Okay. All right. So find the mean and variance. So how do we find the mean? So mean is the integral from minus infinity to infinity x times f of x. But this guy, if f of x, if x is not within 0 to 1, f of x will be 0. So this is the same as integral from 0 to 1, and x times f of x here is 1 over 2 square root of x dx. Okay, so here you have to be very careful because many students make this mistake. If you still put this guy to be minus infinity to infinity, you might get a very big integral. So don't forget to restrict the integral to some for the non-zero values for f. Okay. All right, so let's continue. X over square root of x is square root of x. So we can pull out the 1/2. This is x to the 1/2. How do we integrate that? Well, you add 1 to the exponent, divided by 3 and 2, evaluate from 0 to 1. So 2 cancel. We have plug in 1, we get 1/3. Plug in 0, we get 0. So the answer is 1/3. So that is the mean. Okay. How about the variance? Okay, so mean is also mean. Variance is sigma squared. Okay, and that's the variance. Okay. How do we compute the variance? The formula is minus infinity to infinity x minus mu squared f of x dx. But usually we don't use this way because you see this formula actually relies on the mean, and you're gonna integrate something relies on the mean. So usually don't use this formula. Okay, let me write it down. So usually don't use this formula. Okay, then what do we use? Well, we use the second moment minus the mean square. Okay, so the second moment is integral from minus infinity to infinity x squared f of x. So restrict to 0, 1, x squared, 1 over 2 square root of x dx. Okay, so can you pause here and try to integrate by yourself first? Are you done? Let's check our answer. So 1/2, put it outside. X squared over square root of x. What is that? It's like x to the 2 minus 1/2 is 3/2. Okay, and then we add 1 to the exponent. That's 5/2 over 5 times 2. Evaluate at 0 to 1. 2 cancel. We have what? We have 1 over 5 minus 0 is 1 over 5. Okay, so because this integral, just x squared, does not depend on the mu, so yes, so that's much easier. Okay, now the variance is what? The second moment minus the mean squared. Second moment, oops, so no need parentheses, minus the mean square. 1/5 minus 1/9 is common denominator, 9 minus 5, 4 over 45. Okay, so that is the variance. Sometimes if they ask you to find the standard deviation, you just take square root of that. 45 is 5 times 9, so something like that. Okay. All right, so that's example 1 continued. How about example 2 continued? Find the mean and variance for the following functions. So I would say this chapter 5, is usually more challenging than chapter 3 and 4. So your exam 3 is harder than exam 1 and exam 2. Because exam 3, you're gonna see the integrals, so all the antiderivative formulas from calculus 2, you need to memorize those. And some of the integration techniques like U substitution, integration by part, trig substitution, partial fractions, you're gonna need to recall your memory for that. Okay, if you need more help, feel free to let me know. Okay, so actually on our course website, you can see the other courses I'm teaching. You can go to my calculus 2 course. So I post a lot of handouts there, and now because I'm posting the videos as well, so you can actually watch the videos. Okay. Let's continue. Mean is e of x. That's the integral from minus infinity to infinity x of f of x dx. That is the definition. But here, when x is less than 0 is 0. So that's why it's the same as integral from 0 to infinity x times e to the minus 2x dx. Okay. All right, so how do we integrate this? Well, if you have 2x and e to the minus 2x, we actually use integration by parts. Okay, so what is integration by parts? Well, you have u dv is ue minus integral v du. I hope you can still remember those. So here, when you have a power function and you have an exponential function, you let u be something you can differentiate and make the problem easier. So in this case, we let u be the power function because when you take the derivative, the degree decreases by 1. Okay, so let me use a different color to indicate. So u is 2x, and then the rest is going to be du. Oh, I think it's easier to keep the 2 with the dv. Do you know why? Because then du is 1 dx. V When you integrate that, you have 2 e to the minus 2x over 2. Sorry, negative 2. So 2 cancel, you have negative e to the minus 2x. So you don't see a fraction. So that's why move the 2 with the in the dv. All right. So that's why we continue. So the integral equals to u is x, v is minus e to the minus 2x minus the integral from, sorry, it's 0 to infinity. Integral from v minus, flip this sign to be a plus. du is dx. Oh. So integral of that is e to the minus 2x over negative 2, right? Okay. So actually this is the same as the limit, okay? For the infinity, you actually need some parameter t goes to infinity is a process. You cannot really plug in infinity, okay? So you can replace infinity by t, and then you let t goes to infinity. So when you plug in t, you get minus t e to the minus 2t plus e to the minus 2t over minus 2. So you can put this minus and over 2. Okay, subtract when we plug in 0. When we plug in 0, because it's x is 0, it's gone. And then when we plug in 0, we have minus 1 over negative 2. Okay, so what is that? Well, that is, let's look at what's the limits of the first one. We have t, e to the minus 2t means e to the 2t actually lives in the denominator. And we have, so when t goes to infinity, what's the exponential function looks like this? So minus 2t goes to minus infinity, so this guy actually goes to 0. Okay, and then so we have minus 0, and we have add 1/2. Okay, now let's look at this guy. When t goes to infinity, t and e to the 2t, which one goes to infinity faster? Yes, exponential function. So here we are actually using the L'Hopital's rule, and because we know exponential function grow faster than the polynomial. If your denominator grow faster, then your fraction is just gonna be going to 0. Okay, so that's why this guy, it goes to 0. Okay, so limit t e to 2t actually goes to 0. If you use L'Hopital's rule, because it's infinity over infinity, you can use L'Hopital's rule. This is a formal proof. Okay, so you're gonna take the derivative of the numerator and denominator. The derivative of numerator is 1, denominator. Derivative of the denominator is 2 e to the 2t. So when t goes to infinity, that's why 1 over infinity is 0. Okay, so that's why we come back. This is 0 plus 1/2, so it's 1/2. The mean is 1/2. Okay, and then how to compute the variance? Oh, it needs the second moment minus the mean square. Okay, so let's compute the second moment. So the second moment, we have so second moment, we have e of x squared. Okay, so it's very similar to what we did before, because it's 0 when x is less than 0, so that's why. And then we have x squared 2 e to the minus 2x dx. Okay, so we're gonna use integration by parts again. Okay, so let's use a different color for it. Okay, so what is u? Oops, you let e. Did I choose red? Okay. let u be x squared and then keep the rest to be dv. So then du will be 2x. v is minus e to the minus 2x. Okay? All right. So the integral is uv minus integral of v du. Oh, and then don't forget we evaluate from 0 to infinity. Okay. Do you see this guy familiar? Do you see this guy familiar? Let me use a different color. So, do you see this guy familiar? This is actually our mean, right? We already calculated that, so we don't need to calculate again. This guy is 1/2. Okay, so let's continue. And this is from 0 to infinity. So that's the same as you replace infinity by t. Okay, and you let t goes to infinity. So it's minus t squared over e to the 2t. Okay, and subtract when we plug in 0. When we plug in 0, oh, it's 0. Okay, so when t goes to infinity, what happened? So when t goes to infinity, we have the denominator goes to infinity faster. So we have this guy is 0. Okay. All right. Oh, sorry, I forgot the 1/2. I still have the 1/2 here. Okay, so that's why plus 1/2 is 1/2. My second moment is also 1/2. Okay, finally, the variance is the second moment, which is 1/2, minus the mean, which is also 1/2 squared. So 1/2 minus 1/4 is 1/4. Okay, so this is the variance. How about if I ask you to find the standard deviation? Well, square root of 1/4 is 1/2. Interesting. The mean is 1/2. Second moment is 1/2. Variance is 1/2. I wonder if the higher moments are also 1/2 as well. You can try to compute the nth moments, the third moment, the fourth moment, and maybe we can conclude whether they are the moments functions are 1/2. All right, so that is the last example of this session. If you have any questions, feel free to email me or ask me during the online office hours. Bye!